Class 10. Today we'll discuss the second part of metallurgy, that is the extraction of aluminium in detail. Okay. So before we start with the extraction of aluminium, let us know about some of the ores of aluminium. As I've already written on the board, it is the bauxite, the cryolite and corundum. Bauxite is hydrated aluminium oxide, as you can see, Al2O3.2H2O. Cryolite, Na3AlF6, sodium aluminium fluoride, and corundum, that is aluminium oxide. So these are the three ores of aluminium. Alright. Now, as I said earlier in the last class, that before we go on with the process of extraction of any metal in metallurgy, we have to convert the ore to oxide form. So the first ore that we take is the amphoteric oxide of aluminium, that is bauxite, Al2O3.2H2O. So we use this ore for the extraction of aluminium. And before we carry on with the process of extraction of metals, we have to convert the bauxite to aluminium oxide. Okay. So we do it with a process called the Bayer's process. Alright. Now this is the Bayer's process. So we rub out the different ores of aluminium so that we can concentrate on the three equations in Bayer's process. This is the conversion of the ore, that is bauxite, Al2O3.2H2O. This is bauxite into pure alumina, that is aluminium oxide. So it involves three reactions. Alright. Now, first we have to know the property of aluminium hydroxide. Al2O3 aluminium oxide is an amphoteric oxide. Means it reacts with acid as well as a base to form. It reacts with acid as well as a base to form salt and water. Salt and water. So this is an amphoteric oxide. So aluminium oxide or bauxite, as we can see here, is an amphoteric oxide. It reacts with the base, that is sodium hydroxide. So we react the bauxite with sodium hydroxide at 150 to 200 degrees Celsius to form, and it forms sodium aluminate and water. It produces sodium aluminate and water. So now, what is the function of sodium hydroxide, or we can also call it the caustic alkali. Sodium hydroxide is also known as the caustic alkali. So bauxite is reacted with concentrated sodium hydroxide under pressure for 2 hours as the first step of obtaining the alumina. So we are changing the aluminium oxide, Al2O3.2H2O, that is bauxite, into pure alumina, Al2O3. And it involves three processes, 3 steps, and then the name of the entire process is called, as we all know, the Bayer's process. So what is the function of sodium hydroxide? The impurities present in the bauxite. So bauxite contains a lot of impurities. So we are removing all the impurities. How? By reacting aluminium oxide with sodium hydroxide, the bauxite with sodium hydroxide. Since aluminium oxide or bauxite is amphoteric in nature, the only aluminium oxide, that is the bauxite, will react with sodium hydroxide. Other impurities will not react with sodium hydroxide. Other impurities like iron oxide or silicon dioxide, they remain unreactive with sodium hydroxide. So bauxite reacts with sodium hydroxide. Being amphoteric in nature, it reacts to form sodium aluminate, the salt, and water. Now the next step is the conversion of sodium aluminate to aluminium hydroxide. Now the sodium aluminate that we get in the first step of Bayer's process, we will react it with water at 50 to 60 degrees Celsius. What do we get? Sodium hydroxide and aluminium hydroxide. So sodium aluminate is diluted with water and crystals of aluminium hydroxide is added to it for the further precipitation of aluminium hydroxide, and this process is called seeding. And this is now aluminium hydroxide is removed and it is dried. And in the last step, what happens is we convert aluminium hydroxide to aluminium oxide. So what do? We heat it at 1100 degrees Celsius. So whatever aluminium hydroxide we got in the second step, we will now heat it at 1100 degrees Celsius and we get aluminium oxide and water. Water at that heat will evaporate and aluminium oxide remains as pure alumina. Now this pure alumina is now used in the process of removing the oxide, that means extraction of metals. Okay? So that was Bayer's process. Now we talk about the Hall's process, that is the dressing of the ore by Hall's process, that is the removal of impurities. So we first react in the Hall's process. In the Bayer's process we reacted with sodium hydroxide, and now in the Hall's process we react the bauxite with sodium carbonate. Okay, now aluminium oxide, that is bauxite, Al2O3.2 H2O, reacts with sodium hydroxide to form again the same product, that is sodium aluminate, water and carbon dioxide. So this sodium aluminate now we reacted with water in the presence of carbon dioxide to produce sodium carbonate and aluminium hydroxide. Now this aluminium hydroxide, now again we do the process, the last process or the last equation or the last reaction of Hall's process and the last reaction of the Bayer's process is the same. So aluminium hydroxide we heat it at 1100 degrees Celsius to get pure alumina and water. So that was the Bayer's process and Hall's process for the dressing of the ore or removal of impurities. Now we come to the actual process of refining of aluminium, extraction of aluminium or reduction of aluminium oxide or pure alumina, Al2O3, the pure alumina out of, we reduce it into pure aluminium. Okay, this is the process. Aluminum oxide or pure alumina that we got from the two processes, Bayer's process and Hall's process. This aluminum oxide, now we have to reduce it to aluminum oxide. And let me tell you that aluminum oxide is a very, very stable oxide. It cannot be reduced easily to aluminum by heating or by reducing agents like hydrogen, carbon monoxide or carbon, because it's a very, very stable oxide. Okay, so the only way we can split this aluminum oxide into aluminium is by electrolytic process, by the process of electrolysis. So this is how we do it. So this is the huge tank, okay, where electrolysis or reduction of aluminum oxide takes place by the process of electrolysis. So we have a carbon lining here. We have a gas carbon lining which is connected to the negative terminal of the battery here. So negative terminal of the battery, the whole entire thick wall of gas lining, carbon lining acts as the cathode. And the anode here, which is connected to, you can see many carbon or graphite rods, which acts as the anode. Remember, anode is made up of graphite rods and the cathode is made up of gas carbon lining in the walls of the tank where the electrolysis takes place. Here we have the tap where we receive the molten aluminium in a container. Alright, so since aluminium is heavier and at that temperature, very high temperature is needed here, so therefore we receive the aluminium, we get aluminium metal. We get aluminium metal in the process of electrolysis in a molten state. Now here we go with the process of electrolysis or electrolytic reduction of aluminium oxide or pure alumina into the pure metal, that is aluminium. Alright. Now we have to know about the electrolyte used. During the process of electrolysis, we always use an electrolyte in a molten, in a liquid state. Over here, we use a molten state at the temperature of 950 degrees Celsius. So what is the temperature here of the electrolyte? 950 degrees Celsius. Now at that temperature, what happens is the fused alumina, we add to it. To fused alumina, we add cryolite and fluorspar. We use cryolite and fluorspar. I'll tell you why we add cryolite and fluorspar later on. Okay? After some time I'm going to tell you. Remember that the electrolyte is the combination of fused alumina, cryolite and fluorspar. Cryolite Na3AlF6, fluorspar CaF2 in the ratio by weight of 1:3:1. Got to remember that. Now, what happens is it dissociates now. Aluminium oxide, the ions present, we got to know. Al2O3 dissociates into, ionizes into 2Al3 plus and 3O2 minus. These are the ions that gets dissociated here of aluminium oxide. Alright? Now Na3AlF6, that is cryolite. Na3AlF6 dissociates into 3Na plus and Al3 plus and 6F minus. The fluorspar, that is CaF2, will dissociate into Ca2 plus and 2F minus. So these are the ions that is present in the electrolyte. So we can see that there are different types of positive ions: aluminium, sodium, calcium. Can you see that? So if you look at the electrochemical series, as we have already discussed in the chapter electrolysis, that aluminium is lowest in the electrochemical series as compared to sodium, calcium. Okay, so aluminium is lower in the electrochemical series, so aluminium will get discharged at the cathode. So the reaction at cathode. Reaction at cathode. Now what happens? Aluminium. So aluminium will go to the carbon to the cathode, that is to the gas carbon lining, which acts as the cathode here. So Al3 plus, alright? Al3 plus will receive 3 electrons. Each ion of aluminium will receive 3 electrons and forms aluminium at the cathode, at the gas carbon lining. Okay? Now, what happens to at the anode now? what happens is reaction at the anode. At the anode now, what reaction takes place? We have negative ions, oxygen and fluorine. We have two negative ions, oxygen and fluorine. And oxygen is lower than fluorine in the electrochemical series. So 3O2 minus how many electrons? 6 electrons. Now 6E minus will give you O. Now O plus O will produce oxygen. So what is the product at the graphite rods? Oxygen. Bubbles of oxygen will be formed. Bubbles of oxygen will be formed. So this is the reaction of at the anode and the cathode. So what are the products at the anode? The product is aluminium. At the cathode, the gas carbon lining, what is formed? Aluminium is formed. And at the anode, that is the carbon rods, the positive carbon rods, we have, what is formed? Oxygen is the product. Alright? Now, we go into the detail of it, a little bit of why things are done this way. Now, as I already told you that why is aluminum oxide or extraction of aluminium done electrolytically? Because the electrolyte or the ore that we use, aluminum oxide or the pure alumina, is very, very stable. It cannot be reduced by either heating or by using reducing agents. So the only way we can split or we can reduce aluminum oxide to aluminium, we are reducing aluminum oxide to aluminium, is by the process of electrolysis. So we do it electrolytically. So now, what are the difficulties? Now remember that the fused alumina, we have to be in a molten state, and the melting point of fused alumina is very, very high, almost 2050 degrees Celsius, 2050 degrees Celsius. The melting point of alumina is 2050 degrees Celsius, and now we have to reduce it. We have to lower the temperature. Why do we have to lower the temperature? Because at such high temperatures, at 2050 degrees Celsius, what happens? The large amount of electrical energy is being wasted, and the liberation of aluminium metal, that we get aluminium, but at that temperature, aluminium will melt and vaporize. So it will be very difficult for us to gather or to collect the aluminium in a molten state. So aluminium which we receive at the cathode will be in a molten state, obviously, but at that heat, 2050 degrees Celsius, the aluminium will vaporize. And how do we reduce the temperature? By adding cryolite and fluorspar. Sodium aluminum fluoride and calcium fluoride fluorspar. We add cryolite and fluorspar to the electrolyte, mainly to reduce the melting point of alumina. It comes down to 950 degrees Celsius, as we had already discussed. The temperature of the electrolyte in the extraction of aluminium electrolytically is 950 degrees Celsius. So that is one of the reasons why we use, why we add cryolite and fluorspar. Okay. Now, the addition of cryolite and fluorspar also enhances the mobility of the ions. Okay, and thus the cryolite in a molten state of the state of subdivision dissolves aluminium oxide, and addition of cryolite enhances the conductivity of the mixture, the mobility of the ions, the conductivity of the mixture, and then it also reduces the melting point of alumina. So these are three reasons why we add cryolite and fluorspar. All right. Now, the layer of powder coke, as we can see, this is the layer of powder coke. This is the layer of powder coke is sprinkled on top of the electrolyte. Why? So that all the heat is trapped, so that heat does not radiate out. So we have to maintain the temperature of the electrolyte at 950 degrees Celsius and a little bit higher, so that we keep the electrolyte in a molten state. If we do not sprinkle the coke, heat will radiate out. So we have to keep on heating the electrolytic mixture. So therefore, we cover it with coke. Another reason why we cover it with coke is, as we all know, the product of at the anode. The product at the anode is oxygen. So now, what happens is, if we do not cover it, what will happen? Since the temperature of the anode is also very, very high at 950 degrees Celsius, so what happens is, at that heat, the atmospheric oxygen will also react with the carbon anode. So to stop the reaction of atmospheric oxygen with the carbon anode, we cover it with coke. So there are two reasons. These are the two reasons why we cover the entire electrolyte with powdered coke. It acts as a lid so that heat does not escape or radiate out, and the atmospheric oxygen cannot come into contact with the hot carbon rods or the carbon anode and react with it to form carbon dioxide. Now another thing that you have to remember here is the carbon rods are being used up. So therefore, we keep on changing the carbon rods. How do we change it? How does the carbon rod get used up? Means the oxygen over here, which is formed at the anode. The oxygen is the product that is formed at the anode. This oxygen is formed in all the anode, and oxygen reacts or burns the carbon rods. So carbon plus oxygen will produce carbon dioxide, isn't it? So carbon is being used up. So the carbon rods, the carbon anodes become smaller and smaller and smaller, because at that heat, carbon reacts with the oxygen that is produced at the anode, and then it is being used up. So we keep on changing. We replace the carbon rods. Is it okay? So these are the few things that you have to remember as far as electrolytic reduction of alumina is concerned. So I hope you understood the process of extraction of aluminium electrolytically. So thank you so much for watching.